Well, my dear participants, today I am going to talk about hypothesis testing with R. So, in this, first I would like to talk in terms of the PDF and then I will come on the source window. So, hypothesis testing is a concept which was mainly introduced by Neyman Pearson, and Fisher was also a main contributor towards these things. So, hypothesis testing usually or hypothesis is nothing but a statement about a population under consideration, and population means actually here we talk in terms of statistical population, and population is always defined in terms of the distributions. So, any statement about the parameter of the distribution is nothing but a hypothesis. Now, there are two hypotheses, one is null hypothesis, another one is alternative hypothesis. So, null hypothesis to be tested is known as null hypothesis and denoted by H naught and denoted by H naught. This is the null hypothesis. This is the null hypothesis. Alternative hypothesis, alternative to null is known as an alternative hypothesis. It is denoted by H1. So, H naught stands for null hypothesis and that is hypothesis to be tested. An alternative to this H naught is nothing but the alternative hypothesis. Then there is a term level of significance. It is denoted as alpha and defined as probability of rejecting null hypothesis when it is true. That is, alpha is equal to probability of rejecting H naught when H naught is true. And what is p value? P value is nothing but estimate of alpha. That is, alpha hat p value is equal to p value. So, these were the some of the concepts which I thought should be defined in the very beginning, so that we can talk about all these things. The first most common test is Z test. Z test, actually, in chemical testing, if you want to decide on the basis of whether a chemical is acidic or otherwise, so you need some chemical procedure, you need litmus paper. So, here litmus is nothing but the test statistic, and the procedure of testing is known as statistical inference, hypothesis testing. So, here Z statistic I am going to define. If Y follows normal with mean mu and variance sigma square, then H naught, the null hypothesis mu is equal to mu naught. Mu naught is some specific value versus H1, mu is not equal to mu naught. And sigma square is known. This is a very important concept, that sigma square is known. Then the test criterion is Z test. However, if sigma square is not known, then the test criteria is T test. So, here we have assumed in Z test that sigma square is known. Then Z statistic is nothing but Y bar minus mu naught. Mu naught is some specified value divided by sigma, which is known, divided by square root of number of observations on which the sample is estimated. So, this follows Z distribution, and this is known as sampling distribution of Z statistic, that is standard normal. Example, this is known as sampling distribution. In hypothesis testing, actually we talk of sampling distribution, and sampling distribution becomes the reference distribution. Whereas in Bayesian scenario, if we talk of Bayesian inference, the sampling distribution of mu, its counterpart is posterior density of mu. So, posterior density becomes the basis of inference, whereas here in classical statistics or in frequentist approach, it is sampling distribution which becomes the basis of inference. Now, we are going to discuss an example. Suppose we have a data on a student's height in centimeter and its standard deviation is known to be 5 centimeter. Although it is a very peculiar assumption, we hardly know about the SD, but we are just assuming this to illustrate the problem. Suppose we want to test the hypothesis H naught mu is equal to 140 centimeter height versus H1 that it is not equal to 140 centimeter height, and alpha is equal to 0.05 level of significance. Actually, this is the probability of rejecting H naught. When H naught is true, it is kept at some minimum level and we optimize the power of the test. So, alpha is equal to 0.05. This is the level of significance. Then we are creating a data. See what we are doing actually, we are going into the field, we are collecting some sample of students and then by some procedure. So, here the first randomly selected student has height 168 centimeter, another one is 170 centimeter, the third one is having 185 centimeter, the fourth one is having 172 centimeter, and fifth is having 169 centimeter, then 158 centimeter, 170 and 175 centimeter. And sigma we have already assumed that it is 5. So, sigma is, since sigma is known, we have to use Z test, and Z test is nothing but mean of y minus 140, this is mu naught, divided by 5, and that is sigma, this sigma 5 is here, divided by, this is nothing but square root of length of, the length of this one, see the length of this 1, 2, 3, 4, 5, 6, 7, 8. So, length of this vector is 8. So, it is 5 by square root of 8. And then we compute Z statistic, it comes out 2.18. So, the two-tailed value of Z is Q norm 0.05 by 2, lower dot tail is equal to false, it is 1.96. It is a well known result in statistics that if our alternative hypothesis is two-sided, then the tabulated value, the quantile corresponding this level, lower dot tail is equal to false, means actually if we make distribution, this is the Z distribution, this is the Z distribution, and this is 0, this is minus 3 and this is plus 3. So, here the area in this region is, and this region is what? Actually 0.05 by 2 is in this region and 0.05 by 2 is in this region. So, the area less than this is nothing but, the whole area is nothing but 0.975, and the area greater than this is 0.025. The area greater than this is 0.025 by 2. So, we have specified this area, lower dot tail is equal to false, means we want this value, and this value is nothing but 1.96. This value is nothing but 1.96. So, that we have got 1.96. 1.96 we have got now. If calculated value is greater than the tabulated value, we reject H naught. So, this is the this is a principle of statistics that if calculated value means the value of test statistic, which is 2.18, is greater than the tabulated value, and that is 1.96. So thus we reject H naught, or equivalently, see, if it goes 2.18, so 2.18 will lie somewhere here. 2.18 will lie somewhere here. So what is the area greater than this and less than minus 2.18? So that is known as p-value. So p-value is twice because this area and then minus 2.18, this area, this jointly is equal to p-value. So we are computing that value. P-value is equal to twice into p norm, absolute value of z test, that is the calculated value of z, lower dot tail is equal to false. So if p-value is less than 0.05, we reject H naught. So what is the p-value here? Using R commands we are getting p-value is 0.029. So which is less than 0.05, hence we reject H naught. So this way we reject H naught. So this is all about Z test. Now we can go to the R commands. See here, this is the data we have created. This is the data. So those values are already seen. Then we are specifying sigma is equal to 5, and then we are computing the value of Z statistic, and this value is 2.18, and the tabulated value is 1.96, which is a well known result, and then p-value is 0.029. So since p-value is less than 0.05, we are rejecting H naught, and hence we are rejecting H naught. So this is all about. Now this is not the real situation. Sigma square is never known in practice in such situations. So that's why t-test is more important, because if sigma is unknown, then we use t-test, student's t-test. Student's t-test was developed by William Seeley Gossett in 1907 and 1908. He published these papers in Biometrica. So here we are not specifying value of sigma, rather we are not specifying the value of sigma, rather we are estimating this, and its estimator of sigma is S, a standard deviation divided by square root of S. So if we make these substitution, estimated value of sigma, then this follows student's t distribution with n minus 1 degrees of freedom. So the t statistic we have computed. T is equal to mean of y minus 140 divided by SD of y divided by square root of length of y. So this is the value of t statistic, and it is 11.59. So 11.59 is much higher than 2. See, its calculated value, this is the calculated value of t statistic. Its calculated value is greater than the tabulated value. Hence we reject H naught, because our tabulated value is QT, not Q norm, it is QT, 0.05 by 2. df is equal to length of y minus 1, lower dot tail is equal to false. So it comes out 2.36. So 11.59 is much greater than 2.36. Hence we reject H naught. So that is mu. What was our H naught? Our H naught is that mu is equal to, we have already defined here, mu is equal to 100, on average height is 140 centimeter, and that has been rejected both using Z test, and now we are using T test. t-test is also rejecting that. So, this is p-value is nothing but 7.99 into 10 raised power minus 6. So, it is almost 0 because 11.59 the quantile, the value of the probability against this will be almost 0. It will be almost 0. So, that is why it is the p-value is 7.99. It is much less than 0.05. Hence, we reject H naught. And we can go into the command line, and here we can run. This is the value of t statistic we are computing. Then value of 11.59, and then we are trying to get the quantile of t 2.36, and then we are computing p-value, and we are printing p-value 7.99 into 10 raised power minus 6. Hence, we are rejecting H naught. So, this is all about t-test. T-test for, now t-test for 2 samples. So, we will go to the PDF again. T-test for 2 samples. T-test for comparing means of 2 normal populations. If y1 follows normal with mean mu1 and variance sigma is 1 square, and y2 follows normal with mean mu2 and variance sigma 2 square, and both are independent samples, then to test H naught mu1 is equal to mu2 versus H1 mu1 is not equal to mu2. See, not equal to mu2 means what? Not equal to mu2 means, actually, not equal to mu2 means mu1 could be greater than mu2 and mu1 could be less than mu2. Both the situations. So, they are combined together and we are writing mu1 is not equal to mu2. So, this whole statement can be written like this. So, this both sided, it is two-sided test, and because of this it is greater than, it is less than. So, that is why it is termed as two-sided test. Two-sided test. So, provided there is an assumption with this comparing the hypothesis, provided sigma 1 square is equal to sigma 2 square. It is the assumption of homogeneity of variance, which is very important, because if we do not have this assumption of sigma 1 square is equal to sigma 2 square, we cannot make use of this t-test. In that situation, we have to go for some other test, that is an approximate test, not exact test. So, I will talk about these things also. Then the test criteria is t-test. So, this is the assumption of homogeneity of variance. One is normality, and another one is homogeneity. This is the normality assumption, and this one is the homogeneity of variance assumption. So, t is equal to y1 bar minus y2 bar divided by SP square root of 1 by n1 plus 1 by n2. So, this follows t distribution with n1 plus n2 minus 2 degrees of freedom. Actually, this n1 plus n2 is nothing but the degree of freedom associated with S1 square, degree of freedom associated with S2 square. So, when we pool the sum of square, here the degree of freedom is, this total is nothing but n1 plus n2 minus 2. So, that comes here, and SP, this is the SP square, pooled mean square, and so SP is equal to square root of SP square. So, here we are reporting SP. So, where we reject H naught if absolute value of t is greater than the critical value, and critical value is nothing but q alpha by 2. Degree of freedom is n1 minus 1 plus n2 minus 1, n2 minus n1 plus n2 minus 1 plus n2 minus 1. So, it is n1 plus n2 minus 2. lower dot tail is equal to false. Or we reject h naught if p value, which is nothing but 2. We are taking absolute value of t because here alternative is two-sided. So that's why it can be greater than mu, it can be less than mu. So that's why we are taking here absolute value of t, and degree of freedom n1 plus n1 minus 1 plus n2 minus 1, lower dot tail is equal to false, is less than the level of significance alpha. Now defining a function to implement the two sample t-test. Although there is a function, there is well built function in R, but I have tried to define a new function on basis of this theory so that one can implement his own test. So here function to implement t-test for two samples. So we have defined 2t. The name of the function is 2t, function y1, y2, these are the arguments, and t-test for two sample. Comment: assume sigma square, sigma 1 square is equal to sigma 2 square. y1 and y2 are the two data vectors. So n1 is equal to length of y1, n2 is equal to length of y2. Then y bar 1, this is the mean of y1, y bar 2, mean of y2, variance of y bar is equal to var of y bar, variance of, so this is s1 square, this is s2 square. So variance of y2, and degree of freedom of error n1 plus n2 minus 2, and sp square is nothing but n1 minus 1 into var of 1 plus n2 minus 1 into var of 2 divided by, so here sp square is nothing but we have tried to define this sp square, so sp square, and then t statistic is nothing but y bar 1 minus y bar 2 divided by sqrt sp square into, this is in under square, square root, sp square into 1 by n1 plus 1 by n2, and p value is nothing but twice of pt, absolute value of t, degree of freedom of error, and lower dot tail is equal to false. So out list mean 1 is equal to y1, y bar 1, mean 2 is equal to y bar 2, var 1 is equal to var 1, var 2 is equal to var 2, sp square is equal to sp square, t statistic is equal to t statistic, and p value is equal to p value. P value here it is the name of the object, and this is the value of the object. T is the name of the object, and this is the value of the object, sp. So this way we can return out, and we are dumping this, and then we have simulated data. Take a data set.sheet to simulate the same data. y1 is equal to r norm 1, r norm 10 observations we are simulating with mean 8 and sd is equal to 2, 10 observations. Then set.seed y2 r norm 12, 20 observations are being simulated, and sd is 3. Here sd is 1, sd is 2, here sd is 3, 12 observations from this thing. Now we use t-test to test y1 is equal to y2 and y2 is equal to y2, and this is the output. Mean of 1 is 8.26, mean of 2 is 20 point something, var 1 is equal to 2.43, var 2 is equal to 5.9, sp square is 4.3, and t value is minus 14, and p value is 8.06 into 10 raised power minus 12, which is, so thus we reject h naught as p value is less than 0.05. This means on average mean of the two populations differ significantly. So this is all about the implementation. Now if we go to the R commands, here we have defined this function. So if we run this whole chunk, it is all defined, and then we can dump this. It has been dumped. So dumped 2t.txt. So we can look into here 2t.txt. So these are the codes of the function which are saved, which are dumped, and we can call them by using source. So these are the functions. Now take a data, set.seed y1. Actually set.seed is why important. Say we are having y1. If we will generate again y1, see first you print this y1. It is 6.7, and if we will run again, see what happens, y1. A different set of values has been simulated. But if we write set.seed again and then we run this command, we will get the same data simulated. So when we write set.seed1 and then we generate y1, we are getting the same data set simulated. So this is the role of set.seed. This is the set.seed, and then again set.seed for y2. So then we are using t is 2t, y1 is equal to y2, and these are the values, and hence we reject h naught because our p value is less than 0.05. So now I have talked about certain exercises. Write a function for one sample t test like above. Use the test to test the data empty cars available with the base R package. Use mpg miles per gallon as response. Use the function to test 2t to test the hypothesis about mean per gallon based on AM, automatic versus manual. So these are the two levels. So you can try these exercises and you can verify these results.